Hi, I'm Conor Houghton. This is Lecture 2 in the Probability and Combinatorics section of the unit Mathematics for Computer Science A. This lecture is about combinatorics. To start by motivating combinatorics within probability theory, I'm just going to talk about probabilities that are calculated basically by counting. Combinatorics is the mathematics of counting. So you'll recall that we defined a probability. It was a map from events to real numbers with properties that meant that it could be used to model probabilities, what we think of as probabilities in the real world. And one of those properties was the probability of the union of two sets, where the sets are non-overlapping. In other words, where the two sets have an empty set as their intersection. The probability of the union of the two sets in that case will be equal to the probability of one set plus the probability of the other. Now, in a discrete sample space, an event like this, so here's an event inside our discrete sample space. It has outcomes made up, it's the set of outcomes A1 up to AK. Well, you can think of that set, or you can consider that set to be the union of the singleton sets, each singleton set containing just one of these elements. So A can be thought of as the union of the singleton set containing just A1, with the singleton set containing just A2, all the way up to the single set containing just AK. And in that case, well, the singleton sets are clearly non-overlapping, and so the probability of the event A is just the probability of this event here, the event just composed of A1, in other words the probability of A1 plus the probability of A2 all the way up to the probability of AK. So what happens then if all the probabilities are equal? So we are in a situation where we're trying to model the experiment where a choice is made and all choices are equally likely. Well, let's call the probability of an individual choice Q. We know that the probability of the whole sample space, so X here denotes the whole sample space, we know the probability of the whole sample space is 1. That was another of the properties we gave to probabilities to make them useful for modelling what we think of as probabilities in the real world. In this case, well, because this is true, well then Q must be equal to 1 over the total number of elements in X. So if you think of taking the probability of both sides here, P of X will just be the sum of the probabilities of all the individual elements in X, and there will be hash X of them, where we're using hash to denote the cardinality. So hash X is the number of points in X. So because the probability of the sample space has to be equal to 1, if all the events are equally likely, each of them will have a probability 1 over the number of elements in X, which I'm denoting here by hash or chicken scratch X. And that means that the probability of the event A will just be the number of elements in A divided by the number of elements in X. And so in this case where all outcomes are equally likely, calculating the probability of an event is simply a matter of calculating the number of elements in the event and calculating the total number of elements in the sample space. Let's look at a simple example. We'll go back to the coin flipping. You can flip a coin 6 times, and we want to know what is the probability that each of the flips, all 6 of the flips, will give the same answer. In other words, either all heads or all hearts. And so here, the sample space, X, is just composed of all the possible sequences. H, 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 and then H, 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 T, and then H, 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 T, H, etc., all the way along to T, 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 T. So each of the elements of the sample space looks like A, B, C, D, E, F. And the A, of course, could be a head, or it could be a tail, and the B could be a head, or a tail, or the C could be a head, or the C could be a tail, etc. In other words, we have 2 possibilities for the first element, first letter in this 6-letter sequence, 2 possibilities for the second, 2 possibilities for the third. There's 6 altogether, and so there's 2 to the power of 6 sequences. There are 2 to the power of 6 elements in X. In other words, the cardinality of X, the number of elements in X, is 64. Now, we wanted the probability to know the probability that all the flips turned out the same. There's 2 sequences that corresponds to, H, 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 and T, 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 T. That means the cardinality of the event that we're interested in is 2. The cardinality of the total sample space is 64. 2 over 64 is 1 over 32. So that's a simple case where we worked out a probability by counting the cardinality of the event that we're interested in and counting the cardinality of the sample space. Now, The art of counting, as I said, is called combinatorics. It's the mathematics of taking some set. The sets might be sets of graphs or other more complicated objects, and then counting the number of a specific subtype of objects within the larger set of objects. Combinatorics also addresses the question of sometimes of how you construct those special objects. We saw an easy example a minute ago. The sample space was the space of sequences of length 6 that could have where each part of the sequence could have the value h or t, and we want to know how many of them there were. That's a simple question in combinatorics. It is actually a very rich area of mathematics, which has surprisingly deep links to number theory, and does have many applications in computer science. Computer science algorithms often are algorithms that try and extract certain types of objects from a larger class, and so you want to know how many of these things you can expect to be able to find, and maybe how you might find them. These are two famous combinatorists. That's Paul Erdos and Bela Balabash. We're going to talk a little bit about combinatorics. It's, as I said, a very rich and extensive subject, so we're only going to do a very tiny part of it. The first object we're going to consider is the power set. We've actually thought about this a little bit already. The power set of a set is the set of subsets of the set. And so in this case here, if we have the set ABC, the power set is composed of the empty set, the singleton set containing just A, the singleton set containing just B, the singleton set containing C, the set containing A and B, the set containing B and C, the set containing A and C, and finally this subset that is actually the set itself, the set containing A, B and C. So if this is the set, this is the power set, and we can just by counting here observe that the cardinality of the power set is 8 in the case here where the cardinality of the original set was 3. In fact, what you might guess from that is actually true. The cardinality of the power set is equal to 2 to the power of the cardinality of the original set. This is true for discrete sets. For infinite sets, it's a little bit harder to know what you mean, but the question of how you interpret what you might mean by 2 to the power of the cardinality of an infinite set is actually part of an interesting branch of mathematics. Now, we kind of gave the argument for why this might be true just a second ago when we were talking about the sequence of coin flips. But a nicer way to do it is to think of a map between the elements of the power set and binary sequences. And the way you map it is, if a subset contains an element, then you have a 1 in the binary sequence, in the corresponding place in the binary sequence, and if it doesn't contain the element, you have a 0. So the empty set has no elements, so it's 0, 0, 0. A, the set containing just A, well, A is present, so there's a 1 there, and B and C are absent, so there's zeros in those two places, whereas in the case of B, the A is absent, and the C is absent, but the B is present. And so B will map to 0, 1, 0, A will map to 1, 0, 0. B and C, for example, will map to 0, 1, 1, because the A is absent, the B and C are present. And finally, A, B, C will map to 1, 1, 1. And so the binary numbers of length, whose length is given by the cardinality of A, count the elements of the power set. And so if you have the cardinality of A is 3, then you have 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. They're all the binary numbers, and of course the number of those binary numbers, remembering that you include 0, 0, 0, is 2 to the power of the cardinality of A. And so that is a nice way of seeing that the cardinality of the power set is 2 to the power of the cardinality of the original set. The next object we're going to look at is the factorial. You probably have seen this before. N factorial is n by n minus 1 by n minus 2 by blah 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 by 2 by 1. It's a function that gets very large very quickly. It has actually nice approximations, the so-called Stirling formula. It counts the number of orders of n objects. So for ABC, the number of orders is ABC, BCA, CAB, ACB, CBA, BAC. There's 6 objects there, and indeed 3 by 2 by 1 is equal to 6. It's again reasonably easy to see why the factorial does this. When you're making one of the little ordered sequences, you have to choose the first element. that could be A1 or A2 or A3, blah, 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 or AN minus 1 or AN. And so if you're making and putting these things in order, you have to choose what comes first. There's n choices for what comes first, but having chosen that, there's now only n minus 1 choices for what comes second. So say we had A1 as the element that came first, well then A2 could come second, or A3, or AN minus 1, or AN, or indeed any of the ones in between, and that gives you the n minus 1, and then you iterate. Now you've chosen 2, there's n minus 2 elements that can come third, and n minus 3 that come fourth, etc. So that's the factorial. Next we want to consider the number of subsets of a given size. So we worked out earlier the total number of subsets, that was the cardinality of the power set, 2 to the cardinality of the original set. And now we're saying how many sets are there of a particular size. So in the case here where A is equal to A, B, C, D, we might be interested in how many subsets of size 2 are there. And you can see here that there's 6. So there's A, B, A, C, A, D, B, C, B, D, C, D. So A, B, C, D has 6 subsets of size 2. And we're using this notation here where we use a square brackets and a superscript to mean the subsets of that size. So A to the R is the set of subsets of size R. And what we'd like to know is the cardinality of that set. How many subsets of size R are there of a set A, where the A has the size n, for example. So our reasoning works much the same as for the factorial. We're trying to make a subset of size R, so we choose a first element, there's n choices of first element, then we choose a second element, there's n minus 1 choices of the second element, and so on. But we keep going, but this time we only want to choose R. So this is the first one, this is the second one, and if you're careful with the numbering, this will be the rth one, n minus R plus 1. You can see that the plus 1 comes because the first element has just n on its own. And so the way to choose in order R elements from n elements is n by n minus 1 by n minus 2 all the way down to n minus R plus 1. And we can write that in a nicer way by basically filling out the rest of the factorial. So this is the thing we had here, and that's not a factorial because it doesn't go all the way down to 1. So we keep going, we go n minus R minus 1, blah, 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 2 by 1. And so the thing at the top will be the n factorial, and the bit we added in, we also put at the bottom, so the bits in blue cancel, and that, of course, n minus R minus 1, all the way down to 1, is n minus R factorial. And so that's the number of ways that you can pick R elements out of n elements. But we're not interested in that because that has an order. We choose the first, then the second, then the third. And the subset doesn't have an order. It's just a bag of elements in any order. And so when calculating this thing here, this is the number of ordered choosing of R objects out of n objects. And we want to then, we've therefore overcounted. So we want to divide by the number of ordered sets of size R. And we just work that out. It's R factorial. In other words, the number of subsets of size R for a set of size n is n factorial over n minus R factorial multiplied by R factorial. This is the thing that we talked about from the choosing, and this is the bit we divide because we overcounted. We counted subsets more than once because we were paying attention to what order we took the elements. We put the elements into the subset, and that doesn't matter. So this is the so-called binomial coefficient. So you've probably seen this thing before. What we've worked out is the number of subsets of length R from a set of length n is n factorial over n minus R factorial, and that's the thing that we sometimes call n choose R, or the binomial coefficient. And these are two different common notations for it. This is the one I'll use. And I think it is the better notation. This one explicitly links it to choosing. It's n choose R, you take n objects and you choose R from them. The place that we also see the binomial expansion, not by coincidence, the binomial coefficient is in the binomial expansion. So if you have x plus y to the power of n, well that's going to be the sum from r equals 0 to r equals n of n choose R, x to the r, y to the n minus r. And looking at that allows us to check that the formulas we've been working on make sense. So the power set P of A, which will be equal to, ignore this first symbol here, it's a typo. So the set of all subsets will be equal to the, well, actually there should be a phi here, an empty set here. So the set of all subsets is equal to the empty set plus the subsets of length 1, the singleton sets, plus this union the subsets of length 2, union the subsets of length 3, all the way up to the subsets of length n. And of course these are all non-intersecting, and so the total number of subsets in the power set will be the 1 for the singleton, for the empty set, the number of singleton sets plus the number of sets with 2 elements, up all the way up to the number of subsets with n elements, which is the set itself, the whole of the set. And so we'd expect the cardinality of the power set, which is here, to be the sum of the cardinalities of each of the set of subsets of length r, summed over all possible r's, starting with r equals 0 for the empty set, the symbol I've missed here, all the way up to r equals n for the subset of size n. And of course that then tells you that 2 to the n should be equal to the sum from r equals 0 to n of n choose r, which might look unlikely at first until you realize that that's exactly what you get if you put x equals to 1 here and y equals to 1 there. And that's all I wanted to say for now. Thank you.